Oh, you. Hello, Jayanta. Nice seeing you connected. Jayanta, do you have a microphone for today? If you do, please answer. If you don't, please type in the chat room. Hi, Janice. Nice seeing you connected.
Nice seeing you too.
Okay. Uh, how was your weekend?
It was okay. Not that much happened.
Okay. No news is a good news. Um, okay. Kristen was telling that she could be on important family meeting, so I suggest we go forward with four of us today. So, as in previous meetings, I will give some introductory material for 20 minutes, half an hour, and then we'll go to the practical aspects. And next time, it is next coming Wednesday, is a very important meeting. So there are presentations. So please prepare your slides and send them to me at least 3 hours. Oh, Kristen is here. Hi, Kristen. Happy to see you connected. I thought you will be on some family meeting because you requested we do not do presentations this time. But if you can connect, it's really great. So let's agree on some time for submission of the slides. So if you meet at 5, then slides are needed by 2 p.m. on Wednesday. And if you send them earlier, it would be great. I did send examples from previous semester, and maybe I was sending more in the past, but I can send more examples how the slides should look like. These presentations are key part of the, if you're taking it not for auditing but for the grade, the presentations are a key part of the grade. There will be total 4, and it's substantial part. So please take it seriously. And if you are just auditing, then the meaning of this presentation is that we do a little recital. We practice. We teach each other to be sure that the skills that we get are inside our hands and brains. And if it is presented from one class attendee to another one, it will be much better than from instructor to class attendees. So the one who presents practice it, the others will just listen to it. So I'm going to share the screen and show some slides. Okay, so we are attending the computational chemistry summer course. It is a little, at least there is an effort to make it a little simpler than regular semester course. Here are some books, and here is the plan. So we are completing the chapter 1, and by the end of the meeting, we all should get general idea what is about the algorithm, how the computer codes optimize geometry, which means find such interatomic distances at which the total energy is arriving to a minimum. Last time it was offered that to complete a little homework on building nanotube DNA and summarize the definition of potential energy surfaces. So thanks to those who submitted, and if you didn't submit, please consider it's. You can even do it while I'm mumbling this lecture material. This is quite quick, especially the slide on definition of potential energy surfaces. The link for presentations still does not have Joanta listed. So Joanta, please log into this website and sign up for the remaining subject. So I'm going to share the link once again. And I understand that we all need skills to complement our research with a little bit of computational effort, and we theoretical parts are maybe considered boring, but without them, it will be like walking with closed eyes. So just a little bit of this background is needed. And the homework for the next Monday includes filling of this table, which we will do during the next 20-30 minutes, which means mimicking the activity of computer when it optimizes geometry by human hand. And another thing that we will do during hour and a half after the background is one of the questions. I'm flipping 2 slides back. It is a question that you has agreed to present, question number 11, atomic models from X-ray diffraction data, WESTA. So we all will try to import crystallographic structure of some simple material, let's say popular in the last few years, lead halide perovskite, and build nanocrystal based not floating atom by atom through Gauss view, but importing structure from the database. So I'm going to go over materials that we did in the previous 6 meetings. So the goal of the course is to complement experimental research with a little bit of computational data results for better comparison, and the course is targeting some minimalistic theoretical background, practical skills of using right software and operating right hardware that leads to getting properties of molecules of material that can be compared to experiment and discussed with colleagues. And where we are right now, we were able to separate electronic and nuclear degrees of freedom and treat electronic part with Schrödinger equation that refers only to positions of electrons as independent variables, electronic wave function that is referred here by Greek symbol phi sub a, and nuclear part can be treated under certain approximation with Newton or Hamiltonian equation of motion for expectation value of nuclear positions, which are referred to as capital R in angular brackets in here. So this is possible to do under approximation that momentum of nucleus approaching zero, not absolute zero, but in comparison to momentum of electrons. It is possible in the limit when mass of ions is approaching infinity, not true infinity like mass of galaxy of sun, but in comparison to mass of electron. So it's mathematically in infinity when mass of electron divided by mass of proton will be a small number. And then we are treating nucleus as expectation of positions. So the goal of today's meeting is to set up an algorithm that explains how positions of nucleus are approaching their equilibrium values. And in order to do it, we need just to agree on arranging the equations for nuclear degrees of freedom in a such way, in the algorithmic way, that they can be processed one step at a time, same as people do homeworks in freshman chemistry, like convert unit, or maybe in even earlier middle school, like divide one number into another one, safe result, then plug it into a certain equation, safe result. So algorithm, sequence of expressions. And we do have everything we need, but we need to reshuffle it, rearrange in an algorithmic way. So when we want to practice the equations of motion for nuclear degree of freedom, and we use them in Hamiltonian form with derivative for position and expectation value of momentum. So for connection between the first equation is trivial, is basically definition of velocity in terms of momentum or momentum in terms of velocity, but the second one includes force. And the force it's a really good point of discussion, but to save time, I probably pronounce all details myself. But in a regular semester course, we stop here and discuss it between audience about the definition. So the force is the reason to change velocity, to change momentum. And the force always goes downhill along the potential energy surface. So if one practices derivative of the potential energy in respect to position, one can discriminate between downhill and uphill. So the minus derivative of Hamiltonian in respect to position is called gradient, and it shows where and how quick one should go downhill in order to arrive to the minimum. So in some sense, what we are doing is to practice the Newton equation of motion with the forces, and we needed to do it in algorithmic way. So a little bit of memories from our high school and freshman physics. Let me, I cannot stop myself. Let me ask everyone, how does one solve the second order differential equations? So what is the typical... Yeah, please repeat.
You can sometimes do it via Laplace transforms, depending on what sort of second order differential equation it is.
Very good, very good. And it is advanced. And in very, very basic situations, like differential equations include derivatives, right? And solution does not include derivatives. Which operation is opposite to derivative?
Integral.
Just repeat. We do not have perfect connection, so just slowly repeat.
Integral?
Yes. So we need to integrate equation as many times as many derivatives as equal to the order of derivatives. If it is a second order equation, we need to integrate it 2 times left and right part over independent variable. And if it is a basic equation without complicated complications, it may bring to solution, right? Janice, do you agree, or you want to?
Yeah.
Okay.
That makes sense.
Yeah, it's not always true. Otherwise, there will be not the course of differential equations will be removed from curriculum because sometimes it doesn't work. But in some cases, it does. So if one takes this Newton equation of motion and integrates it first time and then second time, and one needs to do it carefully, putting the different variables for integration and for upper limit. So on one side, we will get back from derivative over position into from second derivative to first, and if you integrate once again to the no derivative at all, and on the right we will just get constant. If things do not, we will get orders, this constant times polynomial of the order of how many integrations we do. If you integrate once, it will get the factor of independent variable t. If you integrate twice, it will be t squared. Make sense? Janice?
Mm-hmm.
Okay, yeah, thank you for confirming. So if we get this Newton equation of motion, the second derivative of position and gradient of potential energy, and if we integrate it and then represent the solution in finite differences, one can project the position at next instant of time, projecting from initial time to the final time, in case the final time is different from initial just by small increment delta t. By taking the initial value, then momentum times first order of this independent variable times this gradient and factor for the mass and the second order of independent variable. Do you have any connections with your freshman physics or high school physics between this equation and what you see here? If you have a mass, like some object that you release in the gravitational force, gravitational attraction to the center of the Earth, what does it do?
Falls. It has a negative acceleration in the downward direction.
Okay, and acceleration means that velocity gets quicker and quicker linearly, right? And the position is proportional to acceleration delta t squared over 2.
Yeah. Mm-hmm.
Okay, so here we are having nothing but the same situation. So increment in position is initial position plus momentum minus this acceleration times delta t squared. So force divided by mass is acceleration. So this term is nothing but acceleration. So we may want to practice this equation in the algorithmic way. I just released cat from one room to another one. So if we are working with computers, then, and we want to program, we do not have continuous functions. We represent any data as a set of points, finite differences. If you have possible values of positions, possible values of times, they are just time steps. If we have position, it is positions at certain time step. If you have potential, it's value of potential evaluated, found at a certain value of position. So if we accept this concept of finite differences, then the force, the gradient, is infinitesimal change of the potential divided by infinitesimal change in position, right? With minus sign. So it's delta potential divided by delta change in the coordinate. If we need to process the increment in position from time 0 to time t, then we practice this integrated Newton's equation. So momentum times first order time, and then this accelerations times time squared. And this finite differences force will contribute into processing this acceleration. In some sense, what I'm presenting right now partially answers the question of you formulated 2 meetings ago, like, are we going to treat molecular dynamics? What we are doing right now is treating of molecular dynamics. Okay. We will quickly, geometry optimization is an important part of the computational chemistry effort. It is done by several software. There are people who are still improving these algorithms, and we are not going to all possible ways to do it. We are going through. We are making a shortcut, and one of the tricks in our shortcut is that when we will compute how far the position is going to be changed under certain force, we are going to introduce damping factor, which means even if we need to roll downhill so far, we will move a little on a little shorter range. And this trick is needed because we do not want to miss the minimum. Like if we have a minimum point between two hills, if you are going down from one hill and we are going with big acceleration, we pick up large velocity, and we just do it numerically, we can easily miss the minimum and go to the other side. If you put a little damping factor, which will be between 0 and 1, this technical challenge can be fixed. Now, thanks to those who have submitted homework 3, and from now on, in some sense, I'm giving partial key to the homework 3. So here is how I did it myself. So if we do have potential energy of the molecule as function of positions, one can draw it as a surface in the space of these positions. If it is molecule with only 2 independent coordinates, then humans can draw it. In most realistic situations, number of independent degrees of freedom is huge, and it is very hard to draw. So it's not possible for humans to draw. But we can keep in mind the figure like that, and in this setup, the space, the configurational space of possible atomistic configuration has some minima, and the absolute value of energy of one minimum and another minimum can be different, and they have maxima and saddle points. So if motion away from the minimum to the left and to the right increases energy, it is expected to be stable, at least in some conditions. But if one communicates energy for a model to ramp up higher than the maximum, then it can convert to a minimum that is lower in energy. So this arrow corresponds to chemical reaction. So overcoming barrier and arriving to different configuration, different interatomic distances. Like if the distance elongates, it is breaking of the bond. If the distance is contracts, it's forming of a bond. And other spaces can be interpreted in chemical language as quasi-stable intermediates, transition states, and basically all chemistry can be interpreted as browsing in a space of potential energy surface for certain reactants. In some sense, one can represent potential energy surface in a finite differences by chopping the surface on many discrete points, computing the value of this potential energy surface, making a long list, and then sorting, making a sorting as we did last time, the Linux command sort, find such value of potential energy U that is the absolute minimum, and then accordingly find which positions R1, R2, and maybe more coordinates will give us the minimum. If this would be possible, we would not need algorithms in today's lecture. But I'm going to offer a little argument. Or I see a comment from you. When I will finish these slides, I'll try my best. We will try to debug things. Okay. So finding all points representing the surface in the numerical way could be challenging, and instead of finding the whole surface, we need another shortcut. So instead of scanning all configurations, we need to find a shortcut that will come from initial configuration that we have drawn as humans by hand to optimal configuration, and we need to find just one line on the surface instead of whole surface. Why it is needed? Why it is why we need to design such algorithm? So here is something quite simple, and I hope it will be appealing. There is a little table that goes over a couple of popular examples, and for each example of each molecule, we count number of atoms, count number of degrees of freedoms, and then count number of grid points. So if I do want to represent a function, a curve with set of points, what would be the good number of points to adequately represent a simple function? Kristen? If you have microphone. Okay, if you don't, let me ask Janice.
Sorry, what was the question again? I'm just trying to think about it a little bit.
So suppose you have some simple function, and you want to represent it not in mathematical way with equation, but as a set of points in Excel. How many points would you use to, by connecting those, will give a picture, will help you to make difference between like quadratic function and exponential function?
Just as like a ballpark estimate, depending on your difference between each point, I would say like if it's a rather small difference between each point, I would say you would have a larger sample size. But if it's a larger distance between each point, then you could have a smaller sample size. But they still need to be somewhat compacted together to see the actual shape of the function.
So what's the number?
I would say like 50-ish, maybe.
Okay, 50-ish is more practical. Let me suggest 10 as very rough estimate,
sure.
Just because it is easier to compute. So if we have diatomic, like O2, H2, N2 diatomic molecule, and then we can scan distances between atoms and take only 10 distances and put a function. and assume that it is good precision, right? Would you accept this idea?
Yeah, I accept that.
Okay, thank you. So in diatomic molecule, we have only 1 degree of freedom, only distance between atoms, because rotational and translational degrees of freedom do not contribute to properties of a molecule. Now, as only a rough estimate, we will spend only 10 points for each degree of freedom. Now, let's go to a little bit more complicated molecule, the triatomic, like water. So number of degrees of freedom of Cartesian projections, or degrees of freedom, is total, which number of atoms times 3, right? Minus 3 rotational, minus 3 translational. So it will be 3 degrees of freedom, like bending, expanding. And if we spend 10 grid points per each degree of freedom, and each degree of freedom is independent from each other, then to make this 3-dimensional potential energy surface, we need 10 to the third, 1,000 points, which is quite possible. We can do it and put this list in Excel. Dependence of potential energy on the interatomic distances. If we go to the acetylene with 4 molecules, then 3n will be 12, right? Total number of degrees of freedom. And we subtract 3 translational, 3 rotational, we have 6 degrees of freedom. So which will means 1,000,000 points. This is also doable. But if we keep this list further, like how many atoms are in methanol? 1, 2, and then 4, 6, right? Yeah. Then 3n will be 18, and minus 6 will be 12. So in order to represent methanol just as a set of points in like represent potential energy surface, we need 12 zeros, which is like what's a human word for this? 1,000 billion terabit. So it ramps, and if you go to any practical molecule, it will expire just memory of today's computers, because the number of data points to represent even potential energy surface, even for quite small molecules, ramps very nonlinear and quick. So this is an argument to avoid scanning of the overall potential energy surface and design a shortcut that gets from whatever we started to the potential minimum. So we need an algorithm. Okay. And if there are several degrees of freedom, gradient can be written in a multi-dimensional way. It is not a big problem. So which equations are we going to process in this shortcut? We need to, and to save our personal time, we will focus only on the 1 dimension, because humans can design ideas but cannot do quick math in a massive amount. So we will focus on the 1-dimensional problem. So positions of ions at each time step, values of potential energy surface at each time step, differences between potential energy on the previous, on the next and present time step, the gradient, and the change in position due to this gradient, due to the force. And anytime we are going to remove momentum completely, because if you would do molecular dynamics, you would keep momentum and let it move, but with non-zero momentum, with non-zero velocity, it will never arrive to the minimum. It will like rotate around and do some complicated motion. If we artificially remove accumulation of velocity at each time step, there will be no chance other than to fall into the minimum. Maybe not global minimum, but one of the minimum. And we need to repeat calculation of these steps in a self-consistent, cycle-wise fashion. So repeat it once, make a little increment, repeat it again, make another increment, and keep increments several times. So please ask questions if this idea about increments is challenging or if you are against it. So everyone accepts this idea of incremental improvement of interatomic positions. Please raise hands or type something if you're against. 1, 2, 3. Okay, everyone accepts. Yeah, thank you. And probably no one took this course. I'm going to tell a joke that I repeat every year. If you didn't hear it, then it's good. If you already heard it, then I apologize. So about this iterative repetition. So an anecdote, a joke. There was a programmer in one of the companies like Microsoft, and this talented programmer didn't came to office. It's definitely a joke before the quarantine time. So the programmer doesn't come to work, doesn't connect online for 1 day, for 2 days, for 3 days, and then the team decided to check how he's doing and made a delegation, went to his apartment. And then they found that the door is open, the programmer is laying in a bathtub, he is alive, but the skin is blue, hands are shaking, and he's looking on a bottle of shampoo with a text: apply to hairs, rinse, and repeat. So, which means, so at this time there should be a laughter. I can do it myself. So the idea is that if we have to repeat some operations again and again, there is it's unhealthy if they do not stop. We need to design a way to stop this algorithmic protocol, and we will design it in a couple of minutes. So for those. We are not going to be programmers. We are going to just get basic ideas, and maybe in the future each of us may hire programmers or give orders to programmers. So for such situation, one typically converts equations into flowchart diagrams, which are then easily converted into computer codes. And we need to design a flowchart diagram for geometry optimization. In this vocabulary, there will be very few steps, like input and output with like round element, arrow, transmission of data, box, rectangular box for math operation, for implementing equation, and diamond for forking, for conditional processing in one or another direction. And we need this condition to stop the cycle when the success is achieved. So we need to formulate conditions for success and stop procedure when it is achieved. So at the beginning, as an input, we put in initial, like position, interatomic position at time step 0. Then inside, I'm looking on these black boxes, we compute the new value of potential energy. We use it for computing the gradient and increment of potential energy surface, increment of position, and then this increment is plugged in to get new position at new step. So if this algorithm gives change in potential energy smaller than some tolerance limit, which means we are approaching situation when next change in position does not improve, doesn't change potential energy. It means we did arrive to the minimum. In some sense, it is a criterion of first derivative equal to zero, which is criterion of extremum, minimum or maximum or inflection point. And this tolerance limit should be one of the inputs. The step size should be among the input, and this initial geometry should be one of the inputs. If the algorithm works well, then the last position will be our equilibrium geometry, and last energy will be total energy that comes out from Gaussian optimization that we were getting in our previous meetings. But there is a situation when either molecule is bad or algorithm is bad, and through repeating this cycle again and again, it doesn't provide any healthy answer. Like if we make 10 steps or maybe 100 steps and it doesn't converge, we can stop this protocol and tell, sorry, either algorithm or molecule are bad, it's failure, let's do something else. So we are going to apply this algorithm to oversimplified model. So let's assume that we have only one potential energy surface, and let's assume that it has very oversimplified functional form. So as humans, we do know the answer. For this function, the minimum will get r equals 0. But let's play a game. Let's assume that we do not know where the minimum is. We need to use it as to check if algorithm would help to find this minimum if our geometry starts somewhere else. So if you select initial geometry to the left or to the right from the minimum, we need to check that algorithm will bring us to the minimum. And we are going to play that we are little computers. File, new presentation. Save this. So we'll make that anyone with the link can edit. Copy link, done, and open this Google Slides. Okay, and sending the link to everyone. So please consider to look to follow the link. And what we are going to do is to set up initial conditions in such way that they should help us to play that each of us is a little computer. So the potential energy surface is a quadratic function. We need to arrive to the answer r equals 0, but we pretend that we do not know this answer. And we start maybe at -5. The damping factor will, not damping factor, the tolerance limit will be 0.3, and we can even increase it. Initial step, we will move just to start optimization one step towards the minimum, delta r plus 1, and we select time increment delta t equals square root of 2, just to make all calculations easier when t squared will be equal to, and damping factor 0.3. So let me start filling it, and then I will ask everyone one-to-one to perform it, to fill a cell. Okay. So if I'm doing step, if I'm doing first step, we did agree that delta r will be plus 1, so we make one step forward. So the next value of position will be -4. Now here the potential at -4, -4 squared will be 16, and in the previous step it was 25. Now I compute the difference in potential energy at current step and previous one. So 16 minus 25 will be -9. Now I'm computing the gradient. So I put minus, then -9, divide by delta r, which was +1. And this should be just 9. It's undo. So square root of time step is square root of 2, and now time step squared divided by 2. Square root of 2 squared divided by 2 will be 1. And now we compute increment. So 0.3 0.3, we keep minus, and then oh no, the minus is already included into gradient, times 9 times 1. So 0.27. No, 2.7. Please correct me if you see an error. So if we need to go to the next line, so our position on the previous step, it was -4, and we add plus 2.7. Kristen, I'm making a little stop and asking, answering question. Kristen is asking, would it be negative since delta U is negative? There is the minus from gradient compensate this delta U is negative, and therefore here the overall increment must be positive, and it agrees with common sense. So if we go from negative side downhill towards positive, we need to keep positive increment. Kristen, does it make sense? Oh, okay, thank you for approving. So -4 plus 2.7, it will be -1.3, right? So the...
No, that's right.
Yeah, correct?
Mm-hmm.
Okay, now the potential at -1.3. So when it's either to be skilled in math or just use calculator. So 1.3 so 1.69. And then we subtract new and old. So 1.69 minus 16. So it will be minus 14.31. And then we need to subtract to practice this. So minus 14.31 divide by increment in position, which was 2.7. So it will be positive increment once, so the delta t is square root 2 time step, the delta t square over 2 is 1, and now we need to practice all this together. So 1431 divided by 2.7, is it like 5.3? Points per factor times 5.3. times 1. Please check if you identify any error here.
It all looks good to me.
Okay. So it will be 1.59. And then if we go to the next line, so previous value was minus 1.3, and we add plus 1.59, which will be positive 29, right? Oh, yes, 29. So let me check if there are questions on the procedure. Anyone wants to ask a question? No. Anyone wants to practice filling the next cell of the table? Okay, then please. Oh, I see someone is looking at it. Someone is clicking. So we can. Oh yeah, thank you. It is offered to fill the same table at home, starting with a little bit different initial step. Yep, very good. Yeah, thank you for contributing. But from these first few steps, you see that we are coming to smaller values of this delta U. So the next delta U will be smaller, and if one repeats it again and again, it will converge. So let's just, for the sake of the time, skip this exercise right now. But the computer codes do the same procedure. So iteratively going over algorithmic steps until the change in potential energy converges to the small value. Insert picture from file. Okay, it is what we achieved today. And in previous years, we let everyone in class to do few more steps, and in additional steps, one arrives to the convergence. So basically, what we did today, we have converted Newton's equation of motion with some shortcuts into the algorithmic procedure that allows to make a shortcut to convert initial geometry into final geometry. So done with the material, and now let's start practical aspects where we will. The goal is to arrive to this structure, which has several dozen atoms, and it's quite boring to plot them in Gauss-View and Avogadro, especially because some of the atoms are do not have covalent bond. It is ionic bonds, which is challenging to practice in either Avogadro or Gauss view. So for solids, it's hard. For metal organic frameworks, is hard. So for situations with ionic bonds, using databases are more relevant. So let's make a little technical break for like 1-2 minutes, and we will continue our effort with connecting. Let's have two windows open in the communication software. One on the local computer, another on the photon server. And in addition, there here everyone, and especially you, are invited to open to find online and try installing. So I need to type it. So to insert new slide. So we need two new tools. One is Vesta software, VESTA. It is not mandatory. One can do everything without it, but it is quite helpful. And another one is find online the website for COD, crystallography open database. Okay, so let's continue in 1 minute further. Okay, so for connecting to photon, let me go over this, the steps. So in your terminal application, if you are on Mac, or in your mobile extern application, one needs to one needs to connect to the photon server, SSH-1 -y. C, Control V. And please send me an email if you do not have a key word for this procedure for connecting to the server. So edit subject photon server. Gianta, I did send you the word to connect there, and you do need to connect. If things do not work through, please request help. But it is critically important that you connect there. And if something doesn't work, send emails to me, to other classmates. We need to help each other, but it's a critical part. So I'm connecting to this photon server, going to the directory, subdirectory that is assigned for our class. And there I'm going to directory for my name, but if you do not have like Gianta should type mkdir. Gianta, please try to practice it. It's not yet late, but 1 week more and it will be too late to pick up. So it's please schedule time when you will pick up practical skills. Listening will not help. One needs to practice. It's more lab rather than lecture. Make directory and you call it by your name. I'm going to my directory, but you can do to your directory. CD 7. And in order to prevent random disconnection, I put TOP. So here is my directory, TOP. And in another directory, I'm on a local computer. Now, I am going to the browser, to a browser. And they're looking for COD, database. Crystallography open database. So COD is not a name of a fish in this context, but it's so highly likely you are well aware of what X-ray crystallography is from background education, and you have heard about it, but let me repeat what it is. So materials can be split on like gas, liquids, and solids. And solids can be either colloidal nanostructures or periodic materials. Periodic materials means the specific pattern is repeated again and again in space. So the materials are often explored by electromagnetic wave in the X-ray range, which means between UV and gamma rays. And this, like X-ray, like one does scan of a human body in these doctors. So if the material sample is periodic, although most of the X-ray comes through the material, but if it is a periodic pattern, there is a way of, it's not reflection in a sense of mirror, it's diffraction. So it beam that is coming to material is coming out at several different angles. And by analyzing this detector the signal of this diffraction, one can pick up signatures of the material on the simplest way. In more advanced way, so in just signatures, it is powder X-ray diffraction. But if the material is ordered, if there is single crystal, the signatures are so bright and so regular, so that by specific protocol, very much related to Fourier transform, one can reconstruct the positions of all atoms in the structure. So it replaces hand drawing of molecules. Just a second, I see a comment from Gianta. There are available desktop in chemistry building. Chemistry building. Red hole, and there are grad students who will open room and assist if needed. And they are coming to the office in spite of pandemic, so just contact them. There is no requirement to have a personal laptop for this course, and there are a lot of equipment on campus. Okay, so X-ray crystallography. Researchers are having access to this XRD, X-ray diffraction data, and they are depositing to the public databases. This one, COD, is only one of them with maybe 500,000 records, but there are other databases. They are appearing and disappearing with time. Several years ago, there was really great database of Naval Research Lab, but then they departed from public domain. And currently, COD is maybe the best one to start from. So, one click search, and if you know SMILES coding, you may try to find molecules that you need. If you know chemical composition, you may try to find what you need. And here is just an example. So I want to get perovskite, and I want it to include cesium, lead. Yes, I will make it even bigger, and I can do the bigger font. Is it more visible this way? Okay, good. So cesium, lead, and chlorine. And this will be very, very small structure. There are like terrific, very impressive structures available through this database, like metal-organic frameworks used for gas storage and detection, and a lot of exotic structure that humans would find challenge to draw by hand. So after putting the input data, it should be enough here, just click send and practice a little bit patience. And it shows several records. So there are records, some basic information, and reference where it was published. So what we are looking for is quite ancient and basic material. So therefore the papers are like 40, 20, even 50 years ago. And then one is clicking onto this COD ID, so crystallography open database ID. Click there. And it does show the elements it includes, shows some information. So it has some implemented viewer, and below there is a link, coordinates. So we do need to click onto this link. Click, it starts downloading, and then you can save file. What I do, but so let me bring. Okay. I already okay, let me play fair game. Copy -LT download .cif. CIF stands for crystallographic information. And then okay. So just a minute ago I did download this 153.cif. So I do copy this file into local directory, and then I can send this file also to my subdirectory on Forum. So scp 153.cif. And then I need the directory, or Ctrl C, Ctrl V. And I probably mistyped the name of the server, so it's sensitive to the names. Chem and edu. Chem, okay. So more 153.cif. It is text file that one can read and analyze. And at the end, there is a list of ions and their positions, but it is quite different from what we used to do in here. So one can convert it like Babel minus input CIF .cif minus output xyz 53 xyz. It types one molecule converted, more 153.xyz, and it shows unit cell with few atoms. This is kind of information we can deal with, but since it is quite popular activity in material science, there are efficient software pieces that make this processing automatic and help to do it more efficient. First, but not last, if I do Gauss view on the photon, .cif. So it does read this file, and you see here it has this chemical composition: 1 cesium, 1 lead, and 3 chlorines. But optimizing or finding properties of this material in this form is a little strange, because like lead needs to be coordinated with several chlorine ions, and here we have it only on one side. Even if there are some reasonable computations that can be done with one unit cell, it's not very intuitive. So one can read CIF files directly into Gaussian and process things further. And many popular software does open it, but the one of the quite efficient for this purposes is Vesta. So if I type in browser, Vesta CIF. So Vesta Minerals, yes. So this is free software. Let me copy the link. And it is highly recommended to install right away on your personal computers. So the executables, so there is a link. Let me increase font once again. So there is a button download, and upon following all these links, you can see there is a Vesta for Mac, and there is a Vesta for Linux, for Windows, and for Mac. So just click it and open it, and it will install. So it's highly recommended to everyone, and today especially to you. I will not do it right now in front of you because I have already installed it on my laptop, and I will show how to process it, what to do with the software. So I'm going to close the structure that we need to do together in few minutes. So I will close and we change to the file. No changes. Everything from scratch. Okay, so here's the interface of this software, and I'm going to File, Open, and looking for the database record that we just downloaded it from the database. So 153.0.1.1.0. So it's a file that ends with .cif. Let me check if what I'm doing makes sense, and if you're following. Should I be slower, or should I cover any intermediate steps? Because there is a chance that let me ask one by one. Gianta, just type if you have some questions or you are okay for me going further. Kristen? Okay, and on the website of crystallography database, they have link, and there are analogous databases for biological polymers that you may need for your research. Janice? Okay, thank you. You? Okay. Thank you, Janta, for answering. Did you started to downloading this DMG? Okay, yes. So I can hold on for a little bit, so when you will have it installed, and I'm confident you will not regret of installing the software. It's really develops wings and helps to do a lot of materials analysis and research. So, and everyone else is always very welcome. It's not mandatory, but it's very encouraged to download and open this software. So then just from the Windows menu, I open the structure, and it automatically progresses replicas, like copies of the unit cell. So there are lead ion in the center. It's octahedrally coordinated to chlorines, and there are cesium. This stoichiometry is explained by oxidation. So lead is 2+, cesium is 1+, and chlorine is 1-. So when we have 1 lead and 1 cesium, it's totally 3+, and when we have 3 chlorines, it's 2-. So they make stoichiometry. So next step. So I'm going to do maybe 3 steps total, very quick and simple. And those will be expanding to show few more replicas of the unit cell, will be step 1. Step 2 will be exposing explicitly chemical bonds, just to draw lines between atoms. And number 3, saving the expanded structure, which is bigger than 1 unit cell, into XYZ file that we can process with Avogadro or Gauss view and run optimization later. So I'm going to objects. So it's menu tab number 1, 2, 3, 4, 5, and going into boundary. Menu, boundary. Click. And then, so if you think we are going too far, do not worry. We will cover periodic structures in the chapter 3 of at the beginning of chapter 3 of this course. So we will return to it in about a month. Now we are covering them very briefly, and then we will go through periodic structures again with more details. But main idea that this same pattern is repeated again and again, like maybe print on a fabric, print on a dry wall, or some ornamental elements. So right now we do have minimal and maximal x, minimal and maximal y, minimal and maximal z are changing between 0 and 1. 0 means begin of the unit cell, 1 means end of the unit cell. But instead of showing one unit cell in each direction, we can go like 3. And then we click apply. So in x direction, and look here, this red arrow with letter A corresponds to x. It's just a language of crystallographers. Instead of x, y, and z, they like A, B, C for the following reason. When we are speaking about x, y, and z, we assume 90 degrees rectangular lattice. But when one is speaking about A, B, C, they can be non-rectangular. Luckily for this object is rectangular, but it may change. So in x direction, or what they call A, we expanded. Instead of one LED, we have 3 LEDs. Now we can put 3 unit cells in y direction. I click apply, and now it looks more like a thin film. So green arrow corresponds to y. So in x and y, now it is 3 by 3 lead atoms, and all complementary chlorines and cesium. And next, I am going to this boundary thing and add number 3 in z. Z changing from 0 to 3 in units of unit cells. Apply. Now it is 3 by 3 by 3, total 27 cesium, and all remaining fluff to keep coordination and stoichiometry. And then I click OK. Let me ask you, do you have Vesta installed and running, or it's still you are still going through installation? Super, I'm so happy. Yeah, thank you for this confirmation. Excellent. So, and I did declare 3 steps. First, replicating unit cells, which we've done. Next, drawing lines between atoms, because it just helps humans to analyze the structure. And the third, saving in a different format that can be reopened and further optimized. So clicking OK, going out of this window. Now edit, so it's third menu, and going to bonds, edit bonds. So there, right, we are not modifying the structure, we just modifying the way it is visualized. So we may want to add lines representing bonds between different groups of atoms. And I suggest we, in order to add new group of bonds, new group of lines, we click new. New. And let's make bonds between lead and chlorine. And if I click apply, nothing will happen because they are a little far away. But if I modify max length and put some like 2.6 or but 3 just for simplicity, and then click apply, it connects all chlorines and leads with lines. And now you see it's a cubic structure for chlorines and leads, and they form mini cages. So leads and chlorines form these cubic cages, and inside a cage there is the cesium inorganic cation. So we are done with step 2. First step was replicating unit cells. Second was to draw lines between atoms. And the third will be saving in a different format. There is no need to draw lines between cesium and chlorine because it will be connected to nearest neighbors 1, 2, 3, 4, 5, 6, 7, 8. So it's 12. So it will be connected to 12 anions, and one positive charge is slightly connected to 12 anions. So it is not preferential binding to one specific chlorine. It's more like moving in an average field of them. So drawing a line between cesium and chlorines doesn't have much intuitive sense. So it's floating in being attracted to several chlorines, like levitating in the space. Okay. And just for curiosity, right now, if I'm looking on this axis, red, green, and blue, parallel to those, it looks cubic. But if I rotate it in such a way that I will see all three at once, then structure will look hexagonal. You can do this little experiment. So going between rectangular pattern to hexagonal. And this is one of the features of periodic structure. So one can look on the material from different angle, and it will be different crystallographic directions. One can cut surfaces at different directions, and there is a nomenclature, there are namings to speak about these features. So right now it is not our goal, but there are professional surface scientists that tell crystal is cut at the direction 111 or 1000, so-called Miller indices. So step number 3, saving the data. So file, export data, and we can save it as XYZ, PDB. So you see several formats. Let's save it into PDB, save, and at the same time I will save it as I better add the little, I'll tell that it is 3 times 3 times 3, so it's not unit cell but expanded PDB. Stop, not save, export file, export data. Now I do call it 3x3x3 dot pdb file, and I also want to export it in the same 3 by 3 by 3 but as XYZ. Do you want to save hidden atoms too? Yes, I do. There are no hidden atoms. If one deals with biological materials, it considers also hydrogen, and in CIF crystallography database, there are also some ambiguous coordinates. Like for one position in space, there are either one or another type of atoms, but right now we are not in this situation. Here's minus OT. So if I do head of this, oh, it is on photon, sorry. I was doing operations on local computer. So there is this XYZ and PDB files. So we are done with original plan to do 3 steps, and now just let's check if these structures make sense. So I'm going to open Avogadro and check if they are openable, if I can open them on the local computer, and then I will forward them to a photon and check if I can set up optimization job in the Gaussian. So here is the Avogadro file, open. So it can read XYZ. Let's check if it will take PDB. Avogadro by some reason works more efficient with XYZ. But check. So yes, it did take PDB, and it agrees to have this lines between chlorines and lead, and the cesium atoms are not connected. And I can try doing some optimization on the Avogadro, but it's not something reliable. It's better to do it on the Gaussian on photon. Click start. It may, you see it keeps the structure, but it makes bond length smaller because universal force field is originally designed only for organic molecules, but it's not so bad. It didn't corrupt the structure and kept the symmetry, which is good sign. And as process is going, it shows this delta E, which is U in the step I+1 and U at step I. So as optimization goes by, this delta E gets smaller and smaller if system is approaching to the minimum. Okay, so let me oh, I wasn't looking onto. I have the same window as you. It asks, do you want to save hidden atom? Yes, we should say yes. Save hidden atoms. So now I am copying basically everything to photon, and there I will try to open this structure. Just everything to photon. Now going to the window with photon, and we already opened the Gauss view should be open. PS for processes? No, I think it stopped. So let's do it once again. Gauss view. Okay, it did open. And in the Gauss view, I can go and open. So it will take CIF, but replication, which can be important for some chemical investigations, is better done with Vesta. So now I take this structure, multiply it 3 times in and saved as PDB. So it didn't draw the distances, which might be a problem. So I wouldn't use force field if there are no lines between atoms. So later on, when we will practice DFT and different electronic structure options, lines between atoms mean nothing, but here it's better to keep them. So I will save as optimized by Avogadro, and maybe save it as PDB. So file save as optimized Avogadro in format PDB. Avogadro. Okay. Doing file transfer once again. And open Avogadro PDB. Okay, so we can run optimization under this UFF here, but generally for materials including transition metals and these highly inorganic things, the universal force field may be problematic. So I can do it only as exercise. And I need to, in addition to this, we will be finishing very soon. In addition to this, I want to say why universal force field is named this way, what is force field, and how it is connected to lecture material. And then I think it will be enough for today. So I'm going to Gaussian calculation setup. Job type. We can start with energy just to avoid errors, and then do a second job for optimization. We do need mechanics only, and click submit to Gaussian. Would you like to save? Yes. And now optimize. Instead of Avogadro, we'll say optimize UFF Gaussian.com. Save. And for a single point, it should submit the following to Gaussian. Yes. Look on the output. And now we can submit it once again for optimization, which may corrupt the structure instead of improving. So for heavy elements, force field has no guarantee. Calculate. Gaussian calculation setup. mechanics, and job type, instead of energy, we put optimization. And just click submit. Save. I can add number 1 to have difference between different jobs. So it should ask if I want to submit it to Gaussian. Yes. Okay. And now I'm looking forward for a surprise. There is a chance that it will either explode or contract it to something unpractical, or job may fail. So it looks like Gaussian is yet. So there is a button current jobs. So it's still working. And while it is going through this computation, let me bring back the slides and give quick comment. About the definition of UFF. So when we went through our table, when we were pretending that each of us is a little computer, when we were practicing this flowchart diagram, there was a step when we were computing the potential energy as function of interatomic distances. In our exercise, we just plugged in value of distance into quadratic formula. In later steps of the course, the potential for each specific interatomic distance will be computed by the adding together electronic eigenenergy and what we call it V sub NN, Coulombic attraction of nucleus. So by using position of ions as parameter, R capital here and R capital there, and combining these two terms, one is obtaining PES, potential energy surface. And this is a heavy, time-consuming computation for each interatomic position. But for several types of chemical bonds, for several elements like carbons, hydrogens, and oxygens, which happen very often, there was preliminary calculations made many years ago, once and forever, which I'm just going to, for illustration, oh, okay, it's here. So one performs tabulation. So this tabulation that I was advocating to neglect is done when we scan distances between two nearest carbons or two nearest oxygens, or carbon and oxygen that have a certain type of bond, when we know for sure that it is a single bond sp3 or the sp2 conjugated bond. And for such famous traditional bonds, the potential as function of interatomic distances is computed, tabulated, and stored in the memory of computer. And this field forces between typical types of atoms are referred to with a term force field. So when we are using force field, it will be extremely quick calculation. But there are at least two restrictions. So this force field will work only for simple light atoms, like first and second row. For transition metals, starting from the third row, it may give drastic qualitative errors. And second, force field does not describe bond breaking information, because it needs to keep information about type of the bond. If you set up pair of atoms to have a like single bond or triple bond, it will keep it single and triple even if it needs to contract or expand. So for chemical reactions, force field will not work. We gave complicated task to the Gaussian, and it's still experiencing challenges with optimizing this this structure. So
I actually got mine done. So I was optimizing my structure alongside yours, and mine just got done, but it was a failure. So I got a fail message. So
do not panic. Do not worry. It's a standard situation. So force field is designed for light atoms and no no bond breaking, bond formation. So we can right now we need to cover in presentations the periodic structures in a sense of borrowing structure and multiplying it as a standalone chapter, as a standalone skill. And in a month, we will return to periodic structure with much more powerful developed muscles to attack them. Right now, okay. So let me check if there are specific questions that I can answer. Maybe I can go one by one, and here is the priority list for the questions. So I expect that Joanta may want to make a mini presentation, whatever you can pick up and tell on subject 8. So please try just to be a part of the community of the class. Those who are the neighbors for presentations of Mahima, you can try to. So you is very good that you covered this. And Kristen, maybe if Mahima doesn't show up, you can briefly mention about dihedral angles so that we have all materials covered. Yeah, thank you, Janta, for agreeing. So I am expecting slides on the subjects Wednesday 2 p.m. If you want to prepare them earlier and want my feedback, feel free to send them as soon as they are ready. I will assign like midnight time, maybe from midnight to 1 a.m. on Monday and Tuesday to do, and tomorrow, if I have some slides, to go over them and make suggestions. Let's go one by one. Joanna, do you have any specific questions for me to cover right now? If please remind me if you want more materials from the class. I may need to resend the links to recordings. They all are on my YouTube channel. You can browse and find them, but it's better if I send. If I forget, please remind me. I really want to share them. Kristen, do you have any questions?
Slides tomorrow evening for feedback, or that would be like
Super. Thank you. Excellent. Janice?
I have a couple questions, particularly regarding NERSC. Is that something that we've covered so far, or is this something that's a little bit different?
Which one? Which question number?
It was questions number 3 and 4.
Okay. So if one goes onto website of the CCAST, just type in the Google CCAST NDSU. There will be link to request an account, and anyone with NDSU email can get an account on this computer. For job submission, it is a qsub command. qsub and then job scheduler. I can go over it, but it will take another hour if I will slowly present it one by one. If you can pick it up, would be great. And I'm going to share slides from previous years.
Gotcha. I actually do have some examples from Russell about job submissions, creating .com files using nproc shared and doing job submissions through CCAST. So I do have a connection to that. I was just curious if I had to do anything regarding NERSC.
No. What you're suggesting using examples from Russell is excellent.
Okay.
In this aspect, he was and is very helpful, and I'm encouraging you to follow his example and share them with us.
Okay. I was just mainly curious about like what is NERSC, because I haven't heard of that before.
I think we can skip it for now.
Okay.
Otherwise, it will be too much. But it is another cluster that we will use for projects. So I will facilitate opening accounts for all of you in the middle of semester. So NERSC is National Energy Research Science Center, operated by Department of Energy, and it is one of the top 10 world supercomputers that we can do much bigger systems like 1,000 atoms by DFT easily. But I will cover use of this facility in much details myself when it will be time for it.
Okay, gotcha. Sounds good.
So little message to everyone: if you have access to any other supercomputing facility, feel free to use it. There is no, I do not insist that the jobs are submitted on a specific cluster. It's the skills and facilities are different things, and if you have access to other cluster and you can upload jobs there, run it there, and then download back on your computer, you are more than welcome to do it. So I will cover only a few facilities, but everyone is welcome to use anything is available. You?
Yes, I have a question regarding Rust.
Regarding what?
Regarding to the optimization with carbonyl DNA structure.
Okay.
But always there's error when I optimize it with Gaussian.
Okay, can you please share screen? I will be happy to look on it and try to. So I will go to the.
So now can you see my screen?
Yes, yes, I can.
So now I just open the PDB file.
Uh-huh.
Here's the PDB file.
Uh-huh, uh-huh. Hybrid.pdb, okay.
I think this one, but it doesn't show in the screen. So I try to start with calculation.
Okay. Please show how you do it.
It's delayed. So go to set up.
Uh-huh.
So you want to optimize with energy first, right?
Yeah,
Or
energy without optimization. It's to avoid unnecessary use of resources for models that will not. Oh, okay, you have a doublet. I see it right away. Charge multiplicity 0, 1. So it's unpaired number of electrons.
So, but this PDB file I saved.
Yeah,
directly
yes.
from the-
I'm not criticizing, but okay. Let's go to the method. Method. Let's change char. Yeah, mechanics, right? Let's change charge from 0 to 1.
0 to 1. And then
no doublet. Now let's change it to singlet. After you change charge to 1, the singlet will become available. No. Ah, yes. See it now. It yes. And now let's go. Let's submit. Yes. And rename it. Yes. Or some like.
So always have this error.
Click OK and continue. Yes.
Okay.
Yes. Oh, click on log. Log was better, but okay. So it's okay.
Still, yeah.
Click OK.
Okay.
I understand in your setup it doesn't show files, but let's click on the results. And there should be summary. Yes. So it shows total energy. Right or wrong, it is here. So it was not errors, it was warning messages. Which so it's maybe not happy with it, but it keeps working.
Okay. So now I need to open the another file to do optimization.
Just with the same that you here now click Gaussian setup and do optimization. Yes, optimization.
Just, I don't need to open a new file.
No.
Let's go to Gaussian setup.
Yes.
I still need to change the charge and spin.
Yes. Generally, if there are no specific intentions to explore doublets, try to avoid them. So doublets are create problems for computations.
Okay, but this doublet is from the structure, right?
Yes, because likely we miss some atoms, and I will show it in a minute.
Okay. So now simply then submit.
Uh-huh.
Save it.
Mm-hmm.
No. Oh, sorry. Oh. Yeah. So and see the results.
Wait. It should give you. Did it tell you that Gaussian job is complete? Let's.
Where? Oh, okay. Yeah. Oh, terminating. Yeah, with error.
Oh, okay.
Yeah, I remember this error. Yeah.
Huh. Okay. Let me try to do the same.
Alright. Can you share your screen and then
Yes.
I can follow you?
Yes. Janice, we are done with today's meeting. You can stay and watch us discussing things, but it is not mandatory. If you're tired or it's enough, it's only questions and answers session.
Oh, I was actually just about to say that I forgot to take screenshots of my homework 3. I had gotten it done at the end of last lecture, but I never took screenshots or anything like that. I have like the energies from the original attempt on the back of this envelope here in front of me, but I'm currently redoing it right now, and I'm just about to send it to you. I was curious if that was okay.
Oh yes,
like,
absolutely,
did
absolutely.
I just get it late?
No, it's great. It's great. Thank you for being responsible and doing it.
Okay, no problem.
Okay.
Yeah, I will send you a Word file with the screenshots on it in like about 15, 30 minutes. Is that all right?
Absolutely. Thank you.
Okay, super. I'll see you guys later. Okay, bye.
Right. So
I will try to remove all the files that I just created.
I'm just going through your file and screening if there was one of the error messages telling that there are some strange atoms. Yes. Let me change it to regular hydrogen. It's not the things that I typically do, but I think it would be correct to. We do not need hydrogen of special type. Let's just have regular hydrogen. Oxygen. Hydrogen divided by times 2. It's very strange. There are quite a lot of those.
The XY eval, right?
Yeah. It's better maybe to.
It cannot be stable from. I cannot change the XYZ to PDB file. Right? Do you remember last class when we
Oh,
XYZ?
let's try. Let's try
So
to.
we say
Let's
from
try
the
to
Avogadro.
let's try to do the following. Software G. I have JMO somewhere stored. Okay, JMO sh hybrid, and I did copy your file into my subdirectory.
Uh-huh.
And I will just copy. Oh, done? No? I do not want to practice our you and my impatience, so just in case JMO popping up too slow, I'll download the file into local computer. And maybe open it with local JMO. Oh, I think the one from JMO and Photon is working. So I noticed that you decided to do CH2 termination instead of just CH.
Yeah, I think it's two. I think
It shouldn't be a problem. It's not why it's declining to compute, but I think for this uh, zigzag without chirality, just hydrogens would be quite natural. The CH2 can be done for like more complicated chiral. Okay. And I'm going to click Save As and practice patience.
do we change anything? Why do we want to save as?
Pardon me?
Do we change anything? Why do we want to
No,
save as?
no. I just if Babel fails for converting, the JMO is more reliable. Hybrid XYZ dot XYZ. Okay. Now let's see. More hybrid. $266 atoms. This one looks a little shorter, so copy hybrid XYZ hybrid xyz1 vi xyz1. So it is just 260x atoms, which is not too much, not too many. So I think I can fix just erase this strange. So the reason why there are different types of atoms, it is because probably these proteins were created for processing by force field, and there, depending on local environment, they, instead of only carbons, hydrogens, nitrogens, they give labels like if the hydrogen is surrounded by so many carbons, it will behave slightly different, and there is a different force field. So this is not quite ab initio. This is a consequence of people trying to do too many things in force field. So I think we fixed everything. Pardon me?
You make the screen, the window bigger.
I didn't understood.
The command window, could you make it bigger?
Oh, bigger, yes.
Yeah.
Sorry. So I just erased. Erased any place, any indices after hydrogens or nitrogen. So it's only pure type of element. And now if I go back into this JMO, I can reopen this modified file. You see here some hydrogens look like pink and do not have spheres, which is quite strange. But after this hand-made corrections, it should be fixed. So I am looking for hybrid XYZ1, opening it. Aha, look, pink hydrogens did disappear. Now it's better. We will try to save it and run on Gauss view, and if it will not help, the next step will be to change termination of the edges of nanotube to see just hydrogens instead of CH2, because right now it looks like there are H2 molecules between each carbon, and this looks a little strange, not for us as humans and researchers, but for force field. So it may treat this hydrogen-hydrogen bond too seriously and consider it as mandated presence of molecular hydrogen.
So could you show me the previous window? You say the pink hydrogen. I don't see the pink hydrogen.
Just a second, I will resave it as PDB right now, and then we'll go back to the command line. So I did open the XYZ that I edited by hand, and now I'm clicking to save it as PDB. So checking file type into PDB, XYZ1 dot pdb. Hit enter. And now I probably can close JMOL. Now in the command line. So I did just VI this file in the XYZ format, and I carefully checked that all hydrogen has only H symbol. There are no like H1, 2, 3. All like if I look on the previous version before this edit, so it is not edited version. You see it has H2, and there are more symbols like H5, C2. So so I just carefully removed this these things because we do not need it. Now, in the Gauss view, I am going to open the recently created file. Open hybrid xyz1.pdb. So now it looks for me it looks better. And now let's just submit it into Gaussian calculation setup. It still has, it suggests charge multiplicity 2, because here there is a uncompensated phosphorus. So I can try to fix it just by adding one more oxygen, or changing, making phosphorus 4 coordinated. But let's try, maybe it will work first without it. Method. One more. Singlet. And instead of hydrogen fork, we click mechanics. Submit. Action calculation setup. XYZ opt UFF. Save. Run Gaussian. And it looks ready. So I click on the .log, opening. So it didn't bring them close enough, maybe because originally we didn't place them close enough. But it's not bad. It's reasonable, and we can check the results. Summary. I don't remember what was the energy at the previous stage, but this one should be smaller. And right now we can get positive energies because there are some repulsive things. But as soon as we explicitly bring electronic structure, total energy will be always negative. So if you want, if you're just interested, yes, I'm listening.
We run the optimization.
What do you mean?
We run the optimization.
Yes, we did run optimization. At least I believe we did optimization.
You only run with energy.
Oh, okay. Let's do energy then. Once again.
When you run the optimization.
Maybe it will be something. Maybe it will bring it closer and bend. Job. Oh yes, sorry. I thought it was okay. Optimization. Then I'm not surprised it was so quick. Gaussian calculation. Save. Submit to Gaussian. Ah, okay. It shows an error.
Yeah, standard.
Okay. No, I do not want to. We can look. So for editing, I'll better download this file to local computer and edit it in Avogadro, and then do another attempt. So on the local computer, yes, taking everything from photo into here. Go into Avogadro, file, open. Hybrid 1 PDB. Open. Reading multimodal file. Okay. It still has some labels. I don't know. Maybe I have missed to edit them. No, it just gives numbers. So on this side, for phosphorus, it definitely should be chemically. It should be at least OH group. So let's put it. I feel nervous about it. So oxygen. Okay, better. Now it will be singlet in a natural way. And let's let it optimize. Stop. Also, let me save it under different name. File save as.
So you add an optim item in the DNA structure?
The optimizing, yeah, it optimizes both, and let me check if it has double bonds. So I'm going just. It's interesting to see CH2 functionalization of edges, but I'm going to replace it to more simple standard hydrogen for now. We can return back to CH2 later.
You make this screen bigger?
Huh?
You make the screen bigger?
Yes. Yes. So I'm just replacing carbons to hydrogens quickly, and then I will remove unnecessary hydrogens. Clicking on this pencil, click, where else? So I think on this side now they are all hydrogens, and now it is H3, but I will remove this non-necessary hydrogens quick. Now on the other side, carbon to hydrogen. If it doesn't want to be replaced, I just select it and then click, and it typically helps. Click, click. Okay. And this one. Okay, now I'm saving just in case something happens. I'll save as version 3. And I'm going to select and erase. Select, delete, 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 select, delete. It's a little bit of manual labor, but can be considered as relaxation. Select, delete, select, delete, select, delete.
So is it better that we without hydrogen kept at the end?
No. Basically, if you take the one without hydrogen kept, one can take the last terminal carbon and replace it to hydrogen.
Okay, with avogadro, I think when you draw the analysis, there's two options: have with hydrogen or you don't want have with hydrogen.
I do not want CH2 groups. Oh, sorry.
Okay, no hydrogen.
Without hydrogen, it may be problematic as well.
Okay, so we need hydrogen, only one hydrogen.
Yes, and it is not universal. It is only for this zigzag tube, for this tube without chirality. For other tubes, it's like more art than science. Like Svetlana and Brandon Gifford and Sergey were finding for several years how to find correct termination.
Oh, so it's not okay. So this termination for
They,
different.
yeah. For each chirality, it's a different termination.
Interesting.
Oh, you didn't realize it before?
I don't realize before.
Oh, it was a biggest challenge in the computational protocols were standard for electronic structure, but they spent a lot of time just to find right termination, because with wrong termination it creates the trap states.
Oh.
Save as. Now let's save intermediate version 4, just in case if I do something wrong that we have intermediate version. And now let's do another mini optimization. Force field start. So this hydrogen to carbon distance closes. And let's stop and check. This phosphoxide group is corrupted. Let me fix it manually. Oxygen. I put one more oxygen here, and then rotate and remove. I added one and I'm removing one. Okay. And we do not need so many hydrogens. Okay. Optimize once again. Stop. Stop. Rotate. Okay, now we may want to move to bring them in closer proximity, otherwise they do not feel each other. The interaction forces are quite weak, so I'm checking this black arrow, selecting only DNA, and now selecting this hand to move it. So I can either click we need to move in direction of positive y. So I'm changing here y 0.1. Click apply, apply, apply. So it approaches closer. Good. Now I put 0 back here, rotate it a little, and see now they are misaligned along z axis. So I may fix it as well. So click on the hand, and now I want to move in the positive direction along z. 0.1, apply, 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 apply. So they will be approximately in the same space. Okay, and now let's do a little optimization. Start. So there is some motion in the point of where they approach each other. They slightly repel. And now I can stop and move even closer. So move along maybe x-axis in the positive direction. Now it aligns them, but it moves a little further. What if I move it in the simultaneously into y? Closer, and now click onto optimization. Okay, we optimize a little bit. Now I stop and keep moving them closer and optimize more. stop and bring them closer. And now start.
Do you want to optimize the whole system or only DNA?
Pardon me?
Do you want to optimize only DNA or the whole system?
Oh, it optimizes the whole system. In Avogadro, I do not know how to freeze part of the system, but in other software, I know how to do it. Like keep one part frozen and optimize only another one.
So you already select the DNA.
But optimization affects both of them. You see, if you see it, like I try to bring, and see the atoms on carbon nanotubes are updated. I change it as well.
Mm-hmm.
So what I'm doing is not necessary. Ideally, it should find best geometry itself, but it's like evolution theory. If there is a architecture who can help it to find minimal best geometry, it will go much quicker.
Mm-hmm.
So
and also we can start with just optimizing sounds to will be faster or not?
yes, it will be faster, but if you were listening to Sergey and his jokes, sometimes he tells about computation garbage in, garbage out. So if we improve initial geometry, then the final geometry will be better as well, or at least it will reach optimal geometry quicker.
Mm-hmm.
So we just helping ourselves, because humans can direct create the geometry in a smarter way, and then it will let computer to do just fine tuning.
Mm-hmm.
Okay, let's stop, forward it to the Gauss view and check if it will accept this version for now. Save as. Version 5 PDB, and I'm going to the this one, and I will just forward everything from this computer to Photon. Okay, and let's go to the Gauss view. If it didn't close automatically, yeah, it's still here. File, open, version 5, open. And now let's go to Gaussian calculation setup. And go to optimization. So it suggests charging multiplicity 0 and 1, which is kind of good sign that adding this OH group may have fixed the problem. Okay, submit. Oh, it doesn't. I forgotten to bring it to. It was in my other window. So XYZ5 optimize UFF. Save. Submit to Gaussian. Gaussian job completed. And I think we selected optimization, right?
I don't remember. I think the optimization.
Okay, let's check. Let's check. I think it is optimization because in Avogadro we made circumference more elliptical than circular, and here it made it more circular back.
Mm-hmm.
And the DNA fragment is quite close to the surface. Maybe it optimized it a little bit, made fine tuning, and let's check what is the total energy. Summary. I am positively surprised. Look here, before it was huge number with like 27,000, and now it is closer to zero. So it's definitely an improvement. So they like to stay together.
Mm-hmm. Okay. Well, probably the problem is because of the DNA with the end of the DNA is wrong, right? It needs OH.
Yes, termination of DNA, and also yes, I think that this is we did three things: terminal OH group, converting a Ch2 termination to H termination, and mechanically just bringing these fragments into closer physical contact.
Mm-hmm, mm-hmm. Okay.
Okay.
Oh, thank you.
Oh, my pleasure. My pleasure. Any yes?
Will this class cover how to build the DNA block? Because you provide us the DNA structure.
So if you want to build DNA yourself, the quickest thing is to install HyperChem. Let me stop recording and say something not for the record.